Hi kids, this lecture is on the conservation of momentum, which is our next big conservation law of the universe, and it basically says that the total oomph for the total momentum in the entire universe is constant. So let's start with just a scenario here. We've got these two ice skaters on the ice. They both have the same mass, and they're about to push off each other. What's going to happen? Take a second and think about it. Hopefully, you realize that when they push off each other, the skater on the right is going to move to the right, okay? And she's going to move with a velocity v. At the same time, the skater on the left is going to move to the left, and she will have a velocity of negative v. Provided they had the same mass when they started, they should have the same velocities when they push off each other. Okay, so the law of conservation of momentum states that in the closed system, momentum is going to be conserved at any moment in time, just like we saw mass was conserved in our last unit. What this means is that if I take the total momentum in a closed system before, it's going to be equal to the total momentum in the same system with the same objects after. You'll notice that I made a closed system from those two ice skaters. It's okay to make this a closed system because there aren't any external forces pushing and pulling on the ice skaters. They're on ice, which is a relatively low friction surface, so the ground isn't even impacting them all that much. And the only forces that are acting are internal. That's going to be between the two ice skaters, both of whom are in the system. You'll notice that the systems do look a little different. Before, we have the two ice skaters together in the middle of the ice, and after we have the two ice skaters moving backwards as we predicted that they would do. So if we take a little moment to think about what the total momentum in this system is, we'll remind ourselves that momentum, or P, is equal to mass times velocity. In my before system, we have the mass of two skaters, but the velocity is actually 0 because those two skaters are both at rest in the middle of the pond, which means that the total momentum is 0 as well. We have mass times 0, we end up with 0. So if we believe in this law of conservation of momentum, that means that my after system also has to have a total momentum of 0 so that momentum can be conserved. Now this feels a little bit weird because we know that those two skaters are moving. Each of those skaters has momentum individually. However, if you remember that the direction of momentum matters, you may realize that while that skater on the right has positive momentum because they're moving in the positive direction, the skater on the left has negative momentum because they're moving in the negative direction. And the amount of positive momentum the skater on the right has is equal to the negative momentum the skater on the left, which means that if I add up all those momenta in the system, I still get a total momentum of 0, and that shows me that my momentum is being conserved. Okay, so let's try a little bit of a trickier one here. We've got a big football player, also on ice skates, and he has a big mass, and a little girl, also on ice skates, with a little tiny mass. What do you think is going to happen when these two people push each other in the middle of the ice rink? Hopefully, you guys came up with the conclusion that that little girl is actually going to fly backwards at a pretty high velocity. Okay, but the thing that will also happen at the same time is this football player is going to move backwards himself at a velocity as well. His velocity will be negative, opposite direction from the little girl's velocity, and it will also probably be a lot smaller than her velocity will be. This is probably just what you guys would have predicted based on your own intuition, but as we'll see in a minute, the law of conservation of momentum is the reason why we end up having the differences in the sizes of those two velocities. At this point, I want to point out something really important, and that is that we've been talking a lot about conservation, and mass is conserved and momentum is conserved, and one of the main errors that I see students make in these kinds of problems is to assume that velocity is also being conserved. Okay, now as we just saw, the velocity can't possibly be conserved. That little girl is going to fly backward with a large positive velocity, but the football player, even though he's going to have a negative velocity, it's going to be a much smaller velocity. If you added those two velocities, they're not going to cancel each other out. So things that are conserved, mass, momentum. Things that are not conserved, velocity. So let's take a look at how conservation of momentum applies here. Again, even though we have a large mass and a small mass, the total momentum in that before system is going to be 0 because despite the fact that they have a lot of mass, they have no velocity. Any number times 0 is going to give me 0, which means that my after system also has to have a total momentum of 0. So how does this work? Well, the little girl has a small mass and a large positive velocity. So m times v, little m times big V, is her momentum. The football player has to have an equal and opposite negative momentum so we can keep the total momentum 0. But he has a large mass, which means that to compensate for that, to keep those momentums equal to each other, he has to have a very small velocity so that the product of those two numbers, mass times velocity, will be equal in size, even if they're opposite in direction. So a quick summary. If we have a closed system, no forces coming in or out, momentum, which is mass times velocity, in the system is going to be conserved. That means it's the same at every moment in time. And the way we find the total mass of a system at any moment in time is by adding together the momenta of every object in the system. The systems we've been looking at just had 2, but you could do this with any system with any number of objects in it. And one really important thing, don't forget that the objects moving backwards have negative velocities and then also have negative momenta. If you forget about this, then law of conservation of momentum is going to be really challenging. So backwards, negative velocity, negative momentum. So I've got one more what's going to happen for you guys to think about before class. I have an asteroid with a mass m, and then I've got a bigger asteroid with a mass 10m on the other side. That big asteroid is moving to the right with a velocity of positive v, and that little asteroid is moving to the left with a velocity of 10 times v and negative because it's going left. So my question is, what's going to happen when those two meteors collide? If you come and show me your solution, including the systems and the calculations that prove it, then I will be happy to give you a good hearty handshake and a sticker. Yay! Everybody loves stickers. All right, see you soon.